So I want to be a little bit clearer with what I should have done here. When you're calculating the potential at a particular point, you're calculating that potential due to each of these charges. Let's call it the fictitious charge here and the real charge out there. And so if I want to calculate the potential at this point, what's important is this distance and this distance. And here I already supposed that the charge is negative, and I didn't take it into account over there. So let me come back to what would, let's say, make more sense. What I've written here is correct if Q is not known at all, the sign or the magnitude is not known, and A is not known at all, right? It would just be, well, I've supposed that it's positive, but when I solve it, I might discover that it's on the other side of the origin, right? But I have a specific thing that I've guessed there, so let me write in the specifics here rather than writing it like this. First of all, I supposed that the charge was negative, and so I should appropriately label that guess there as negative. Yes?
Did you also switch the A and the B's under them?
We'll get there.
Okay.
Right? This is correct. All right? This is correct. But if you actually look at this distance here, from here to there, is B minus R. All right? B is greater than R, so I could equally well right here. I don't have to fiddle with the absolute value. I could have written B minus R. And then I can look here and say, okay, what am I really talking about here? I'm talking about that distance there, which is R minus A. So rather than the absolute value in here, I could write R minus A. Similarly, on the next part, I could look at it and say, well, what distance am I really dealing with here? I'm looking over on this side here, and this distance is R plus A. And over here, this distance is R plus B. Now I'm not worried about keeping track of absolute values, squaring things, and all of that sort of business. I don't have to worry about that. I actually, by looking at the actual problem and figuring out what the distances really are, I don't have to write it down in the generality that I wrote it down before. Okay? So this is the real problem that you've got to solve. And you'll find out that, oddly enough, Q, little q, has a smaller magnitude than big Q. And you could even look at it and guess what the ratio of the charges has got to be in order to make the potential 0 at that point there. Right? And it'll depend upon distances, but you can figure it out. And then with the second equation, you can figure out what the distance has got to be. Okay? All right. Yes?
I'm still confused as to why it's B minus R under little q, because that's the distance to big Q.
Oh, that's what you meant.
Yeah.
What did I say?
You said you'd put it off and address that later.
Oh, crap. I messed this up. Actually, what we should, yeah, here, I'll put it back the way it was. Wait, I already switched this one up. There. Okay? Okay.
Sure.
Magic of chalk. All right. During break, I was asked another question, which was, couldn't we just solve this using the series solution of the Laplacian in that region of space out there? And the answer is absolutely yes. Yes, we can. There's a button to that, which is that the solution that we're going to get here actually comes out and looks very pretty. It's really just the potential. Looks like this. Well, actually, I'm going to have an X, Y, and Z in there by the time I'm done, or an R and theta, for example, by the time I'm done. But, sorry, R and Z by the time I'm done. But this sort of has the physical content of what's going on is elegantly shown here. When we do the solution by series, we'll certainly get a set of equations, or rather a set of relationships that's going to be true, and it's going to give us the potential from which we can calculate the field. But you won't be able to just look at that and say, oh, that's just that, right? If you can guess something using the method of images, and it takes a little bit of analytical work to do, by the time you're done, you have a good idea as to what's going on in the problem. Whereas very frequently when you solve something either numerically by the method that I gave you last class, which is the relaxation method, mean value theorem, you definitely get the potential. But all you can do is look at it, and then you try to deduce some things like which way does the field point and how strong it is. But you don't get a sense of, let's say, the elegance of the underlying mathematics of this course. So the method of images is to give you a better idea of what the answer looks like physically. Right? But when you can't guess a solution, come up with a solution that works by the method of images, and you only know the potential on some boundaries, so you can't do the straightforward calculation of the potential from adding up charges or integrating over the charge density over the distance. So those are our two brute force. Well, the first method is the brute force method. If you know the charges, you can just solve for the potential. It might not be pretty, but you can just solve for the potential. You can guess something by method of images. I say guess, but I mean you have to make some clever analogies and try to figure out what's going on in a problem by the method of images. That's another approach. And by the way, the method of images that I showed with the spherical surface, if you look at that as an optics analog, you'll find that the ratio of the charges and the ratio of the positions and all of that works out as it would be if you had an object and its image. Right? So that's why it's called the method of images. And so you can solve many kinds of problems by sort of knowing what the equivalent optics problem is like and then making a guess about what the charges should do.
Imagine that alternates in optics.
One of the neater, more complicated problems in the method of images, not very complicated, but it's neat, I've given it on exams, is this one. Two grounded planes. I'm not going to solve it.
Aww.
It's really easy. Two grounded planes, and then ask what's the electric field between the two planes. Some of you might, how many of you took optics? Oh, actually I might have done this in honors physics too as well, right? But if you took optics then, so I'll just tell you, put a minus charge here, that's the image. Now you look over at this guy and you take the image of the image. Now you look over here, you take the image of the image. Wait, what? The image of the image of the image. And you just keep going.
Oh,
Why wouldn't you
like
also
two
do it on the other
mirrors
side?
across from each other in an elevator.
Yes.
Those are cool.
So this is one that you really would not want to solve by series solution. But it's beautiful when solved this way.
Aren't you creating a series?
Yes, it was a different series that we're solving. And this series converges. The other one probably does too. I would have a test. It's got to converge.
You gave that one for homework as well.
No. It was an entirely different class.
Oh, it is?
Yeah.
Yeah, okay. So, now for some math, a mathematical interlude. There are classes of differential equations that look like this. If I have differential equation in general, it looks like this. It looks like that. Okay. That class of equations are called Sturm-Liouville equations. Do you cover those in differential equations?
Nope.
How many of you have heard of Sturm-Liouville equations before? In mechanics?
Nope.
It turns out, where?
In the 4,000 level ordinary differential equations class.
Yeah, so that's an elective.
Yeah.
All right, so if you're a math major, you would have seen this. It turns out that let's remove the virtually. Every physical problem is the solution to a Sturm-Liouville equation. It's just a question of how complicated the P of x, Q of x, and R of x are. I just lied. That's the differential equation. We need a set of boundary conditions in order to define the problem. Right? And so, with a boundary condition, A1, some constant, y at some position plus a constant y at y prime at that position. That's one boundary condition, set of boundary conditions. And B1 y of b plus B2 y prime. And b is equal to 0. So I've written this down as a one-dimensional problem, and I have said that I have a set of boundary conditions that apply at position A, and these are just constants, right? And a set of boundary conditions that apply at position B. And if I can express the problem in this way, so that it can be, so that the differential equation that I need to solve has that form in general, then and has to satisfy some set of boundary conditions like this, then that's a Sturm-Liouville problem, right? It's quite clear that this, let's just write d squared 5 dx squared equals 0. That's a Sturm-Liouville problem, right? All I've done is to set p of x equal to 1, and q of x and r of x equal to 0. So that's like the simplest Sturm-Liouville problem that you could suppose. Okay? So I'm using that name again and again. The solutions to these kinds of problems have some very special and wonderful, wonderful properties. So there is some set of solutions, y sub n of x. Some whole bunch of solutions, right, that are called the eigenfunction. equation of that system, right? N is an integer, 1, 2, 3, right? It just indicates which solution it is that we're talking about. And these solutions only exist for certain eigenfunctions lambda. Eigenvalues lambda. So there's a set of lambda of n corresponding to each y of n. All right? So I put a y of n in, and then I find out which lambda of n satisfy. Now you look at that equation and say, wait a minute, that doesn't look as though I'm going to get a lambda of n in there. It's going to come in here when I start taking derivatives. And those solutions, first of all, those are solutions, but they have a couple of very special properties. One is that the y sub n of x are orthogonal. With a certain weighting function. It'll turn out that our weighting function for Laplace's equation is 1. All right?
Or
Meaning-
normal with weighting?
Well, not done yet. They're orthogonal first. All right? Then they're orthonormal. That's, you see, normal, let me write it down, okay? This is with the appropriate, so actually, let me write. We're sure they're orthogonal. With the proper weighting, then they're orthonormal as well. But I have a weighting function here, so I'm mostly concerned with the form. So what you said is right, Ryan, but here, if I just multiplied by some function of x without care for any constants, then I would have orthogonal but not necessarily normal. Okay? Orthonormal with the right weighting function and constants. What do I mean by that? I mean that the integral over the interval from a to b, because I've defined these boundaries, a and b, and I only know the solution between a and b in this case. All right? The integral from a to b of the appropriate weighting function, which is r of x, that r of x over there, okay? Of y sub n of x, y sub m of x is equal to 0 for m not equal to n. And if I put the appropriate constants in, multiplicative constants for r of x, then it's equal to 1 for m equal to n. This is what says that these functions are orthogonal to one another. Just like vectors, if I perform the integral product, which is scalar product, of these two functions, then these behave as though they're orthogonal to one another. Right? And if m equals n, and I've got the right weighting function in there, then this integral is just going to be 1. That's a really useful property of some set of functions, right? But wait, there's more. First, let me tell you what's more. There's one more property here. These solutions, once I've found them all, are complete. Meaning that I can't find another function not made up of those functions for which that's orthogonal to those, that I found them all, right? And that actually means that I can use that complete set of functions to add up and make any other function in the space. You've already learned about this. The one special case that you've learned about is the Fourier series. all right? Sine of x, sine kx and cosine kx on an interval in space, all right? And in quantum mechanics, you found out you can describe any wave function in that space by, I assume, yeah, you've all had quantum mechanics at that level, right?
Mhm.
Good, okay. You can describe any function in that region of space as the sum of sines and cosines for a constant potential. You've actually just solved that problem. Okay, so now let's deal with some special circumstances. Now, Robert, yes.
I'm just curious, are the R of x in the Sturm-Liouville equation
Yes.
and the weighting function the same?
Yes.
Okay.
So almost the first thing that you do when, well, okay, first thing that you do when faced with the new differential equation, right, is to actually ask whether you've seen it before. And the second thing that you do is look in Schaum's outline. And by the way, there is a 3 pages in Schaum's outline that just says, here are the special functions. Special solutions to differential equations. Bessel function, Legendre polynomials, all the special functions that you know about are in there as solutions to Sturm-Liouville problems, right? So every set of solutions that you've learned about so far has those properties. And every set of solutions that we're going to learn about in this class have those properties. And what that means, by the way, is that I can always express the potential in some region of space if it satisfies Laplace's equation, the Sturm-Liouville problem. If it satisfies Laplace's equation, I can always express it as the sum of sines and cosines, the sum of Bessel functions, the sum of Legendre polynomials. All of those work within a, well, in all of those cases, there are certain boundary conditions that have to be met and the limits over which we're going to find our solutions, right? Once we've identified the boundary conditions and the limits, any of those sets of functions works, right? It's a question then of actually guessing the right sets of functions that make the problem be interpretable to us, right? And also leads to some convergence in the end on the series. Okay, so now we can talk about the separation of variables approach to the solution of the problem. And I'll just assert that all of our solutions are going to fall into that Sturm-Liouville equation system, relationship. And then you can test for yourselves whether that function, that differential equation that I just wrote up there and didn't erase yet, and the is recorded.
It's on YouTube.
Applies to our set, to our problem, right? So let's start out with Cartesian coordinates. And that's going to apply to any situation where I have rectangular boundaries of some sort. And what we generally do, we've got a differential equation. Just del squared phi is equal to 0. But in Cartesian coordinates, I'm going to assume that the solutions can be expressed in x, y, and z coordinates most easily. So I'm going to suppose then, and this is what you do in the separation of variables approach, that phi of x, y, and z is equal to, how am I going to write it? A function of x times a function of y times a function of z. We don't know that that has to apply yet, but we already do because you've solved the problem many times already. Well, we're going to suppose that, and then we're going to find out what conditions apply that give us a satisfactory solution. And I guess I should have commented at the start here, that anybody who's like a dual math major here should just sort of, I don't need you to raise your hand. Only nerds raise their hands when I say that.
Thank you.
Any of the dual majors or anybody who's been through the math modeling contest or whatever, just keep your mind shut down whenever I say something that is completely unmathematical, right? I do math, if I had sticks that I could put gloves on 5 feet out, then I'd be doing it with my hands 10 feet out, waving them all over the place, right? I'm just invoking mathematics here. And that invocation works really well most of the time. Every once in a while you get into real trouble. I get into real trouble. And then in my particular case, I walk next door to Professor Siegman and I tell him what I've done and he stands there like this. And then he says, you should have done this. I say, good, thanks, goodbye. But 99% of the time, I'm okay. Did you say 5? 5. Okay. So there's my equation there. Now I can just write it out. And that means that I've got, substituting this, I've got yz d squared x dx squared plus xz d squared y dy squared plus yz, whoops, x, y, d squared, z, dz squared. Right? And then I do something that I have to impose some mathematical conditions on in order to do, but I'm just going to go ahead and do it. Right? I divide through by x, y, z, hoping that it's not 0. And sometimes it is, but we're going to ignore that. This is the point where Professor Siegman's going, right? But it's okay. With me. It's okay. There. Right? Each of those is solely a function of x, and solely a function of y, and solely a function of z. What I could do is go through this problem and isolate term by term and say if this side is a function of x and y and that side's a function of z, then both sides have to be equal to a constant, and this side and that side and so on. Instead, I'm going to jump to the bottom line here, which is that each of these must be equal to a constant. And I'm going to write those constants as alpha squared, beta squared, and gamma squared. And that says that the sum of those three constants has got to be equal to 0. All right? So d squared x dx squared, 1 over x d squared x dx squared is alpha squared. Same for y, same for z. All right? There's a little bit of a problem that we see here, which is that alpha squared plus beta squared plus gamma squared has got to add up to 0. If they're all real, we're in trouble. Right? So at least one of them has got to be complex. Which one is complex actually really doesn't matter mathematically. But when it actually comes down to solving the problem physically, we want to try to guess which one's going to be the complex one and which one's not going to be complex. Right? I'm going to do a problem as an example, a specific problem as an example. And I'll that. Ah, there's my chart. There's my eraser. That's what it's called. Let me solve, it's going to be a three-dimensional problem, but I'm only going to draw it in 2 dimensions.